Hello everyone. Today we're going to be talking about a tool that people doing trigonometry can use to visualize things in their head, and it's called the unit circle. And before I get into what the unit circle actually is, I want to first remind you of our trig functions and their definitions. So sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. And of course you could get these from any triangle, but what the unit circle centers around, its specialty is getting these values from a triangle of hypotenuse 1. So say you have your triangle here, and the hypotenuse is 1, and then this is your angle theta, this is your opposite side, this is your adjacent side. Since hypotenuse is equal to 1, therefore sine theta is going to be just the opposite side. Cosine theta is just going to be the adjacent side. And of course tangent theta will still be opposite over adjacent. But there'll be something you might notice here, which is that this is similar to this and this is similar to this, but I'll pick up on that later. Alright, so the unit circle is basically a graph of a circle going outside from the origin with a radius of 1, because it's a unit circle. And the way we figure out the graph of this is, of course, that for any x point, the distance between here and here must be 1. So if we call this the delta x and the delta y, you get a right angled triangle where this is 1, and so this is the x coordinate, this is the y coordinate, and 1 squared must equal x squared plus y squared as per the Pythagorean theorem, and so the unit circle is the graph of x squared plus y squared is equal to 1. Now, the way the unit circle is used stems from the fact that you can also draw a triangle in here from the radius, because the radius here is acting as the hypotenuse for this triangle, and so if this is 1 and this is angle theta, the distance here, which is the opposite side or the y coordinate, it's going to be sine theta. And the distance here, which is the adjacent side of the triangle, and the hypotenuse is 1, so it's going to be cosine theta. And so at the unit circle, for any theta here, this point here where it reaches the circle, it's going to be of the coordinates cosine theta, sine theta. Now, what can we do with this information? Before, it was kind of under the assumption that trig functions could only take inputs from 0 degrees to 90 degrees. And why would we have thought this? Well, this is because there is no such right-angled triangle for which one of the angles can be outside of this interval, or even 0 degrees or 90 degrees in fact. However, with our new definitions of sine and cosine and the fact that the unit circle is like this, we can sort of extend it forever, basically. So what you want to do, if you're taking an angle which is greater than 90 degrees, you can just keep rotating this radius around the unit circle. For example, if you took the radius, or if you took, awful diagram here, if you took the angle theta to be 150 degrees, you would rotate 150 degrees around here to get the line here. And this triangle, you want to go from the second line of the triangle, you want to go down from the point to the x-axis, and then you want to go back to the origin. That's how you figure out where the triangle is going to be. So like, I'll touch on that in a second, but basically this angle theta, which is 150, you're left with this triangle, and the coordinate here is going to be cosine theta, sine theta. And that's the coordinate. And we know this triangle is going to be 60, 30, 90, a 60, 30, 90 triangle. And we know this side here is 1, this side here is half, and this side here is root 3 over 2. So since the x-coordinate is root 3 over 2 on the left-hand side of the origin, we know, for example, that cosine 150 is equal to negative root 3 over 2, or that sine 150 is equal to 1 over 2. Positive 1 over 2, in fact. And the way you know how to draw these triangles is sort of like a bow tie pattern. So I'm just going to draw some sample triangles for all 4 quadrants of the graph, and it'll look something like this. The triangles will always go from the origin to the point on the graph, to the point on the line, and then back down to the x-axis, and then back to the origin. That's the key here. So here, 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 and yeah, basically that. Now, theta can be also outside of 0 to 360 degrees. Theta is not limited to this interval of 0 to 360 degrees. In fact, theta can be any real number, because in this thing here, if you rotate the full way once, that's apparently 360 degrees, or in fact it would be better to put the arrow here, because you are in fact rotating this way through the graph. For example, this is your theta. But the thing is, this 360 degrees, you end up with the same thing as 0 degrees. So you'll know, for example, that sine 360 is sine 0, or cosine 360 is cosine 0, and so on and so on. These sine and cosine functions repeat every 360 degrees, or every 2 pi radians. And on top of that, if you wanted to, say, have a value of 1080 degrees, that would just be rotating 3 full times around the unit circle. And you'll still be left with the triangle, which is just a flat line there. And of course, you would know that cosine 1080 is 1 because you go here, because it's right where you started, and sine 1080 would be 0. And if you want to go negative, of course, rotating theta normally goes counterclockwise, but when you want to go into the realm of a negative theta, you go clockwise. So say this angle here, if this was 30 degrees, then you'd be running with this theta of minus 30 degrees. So like for a triangle here, which would have a hypotenuse of 1, an angle here of 30, 60, and 90. You know, this is 1 over 2, this is root 3 over 2, and therefore, since this is below the x-axis, sine negative 30 would be negative 1 over 2, and cosine 30, for example, would be positive root 3 over 2. And this is kind of how you can get any sine or cosine values from the unit circle. But we're going to talk about this relationship between sine, cosine, and tangent in the next video. But for now, I'm going to wrap up this video with a recap of the fact that the unit circle is the graph of a circle with radius 1. You can pick any angle theta that you rotate from this line facing right, any amount of rotation here, say we rotate 270 degrees, or even 300 degrees. And you can also draw the triangle here to find the values of sine and cosine for any angle, basically. And you can also go into the negative realm by rotating clockwise instead of counterclockwise. So like negative 120 would take you to a triangle here. And for example, if our theta is negative 120 and you wanted to work out sine and cosine of a negative 120, you just take this triangle here, where this is the cosine and it's 1/2 because it's a 90, 60, 30 triangle, where the hypotenuse is 1, that's 1/2, and that's √3/2. And since this is below the x-axis, the √3/2 is negative, and so sine theta is positive 1/2, and cosine theta would be negative √3/2, and so on and so on. So yeah, that's basically how you get sine and cosine of any angle from the unit circle, as long as you're able to identify one of the two special triangles, either the 90, 60, 30 triangle or the 90, 45, 45 triangle as well. And that's how you can find special angles like negative 45, 225, so on and so on. And this works for radians as well. The unit circle is split up into 2 pi radians. Each quarter is pi/2 radians. Each 1/12, say, is pi/6 radians. And this pattern continues for values of theta that are also greater than 360 degrees, because if you're simply rotating by an amount plus 360 degrees, it's the same effect as rotating just by that amount. Alright, so thank you for watching. In the next video, we're going to be going over the relationship between sine, cosine, and tangent.